Hi everybody, in this video I want to do some more examples with square roots. So we've already seen how to simplify square roots and even how to simplify some that are a little bit more complex where they don't come out to be perfect squares. But we haven't done too much more with them yet. So let's actually do some more examples with square roots and get into a few of the harder examples as well and some operations. So in this video, I'm really just going to do a bunch of different examples of different styles. So you can see how to work with roots, again, in a little bit more complicated way. So if you don't just have a single root, or if there's an operation going on, maybe there's addition involved or division or something like that. So how do we deal with those kinds of situations? So I'm going to just start with a couple of still kind of basic examples. So our first set is the one on the left, you have the square root of 9 plus 16, but everything is under the radical. And then on the right, you have the square root of 9 plus the square root of 16. So you actually want to follow order of operations here. And a radical symbol works sort of like parentheses. If you have something underneath the radical that can be simplified, you should always do that first. So here, we're going to go ahead and simplify. 9 plus 16 is 25. And now this happens to be a perfect square, and the square root of 25 is 5. If the root is separated by addition signs, you actually can't combine the inside of the roots together. So you need to do them separately. These both happen to be perfect squares as well. So square root of 9 is 3, square root of 16 is 4. And then 3 plus 4 is going to be 7. And you can see you get totally different answers. So this is really different than some of the examples we've seen already. For instance, when we had an example with multiplication, something like the square root of 50, we were able to break that into the square root of 25 times the square root of 2, right? 50 is the same thing as 25 times 2, and you actually are able to separate back and forth here with multiplication. This is actually referred to often as the product rule for square roots. So I'll just make a note here. Which says that it's basically okay to go back and forth between those two forms. So when you multiply, you can separate it out, you can put it back together, it doesn't really matter, you can go both directions. And then in this case, that 25 happens to be a 5, so our answer becomes 5 root 2 here. This rule is not true for addition and subtraction. So you can't just separate roots out or bring them back together when you're adding and subtracting. So you want to be really careful there as you're going through those examples. Let's do another example with the product rule. So here I have the square root of 6x times the square root of 3x. Now, if I had something that was obvious to simplify, I'd probably do that first, right? If the square root of 6 was a nice even answer, then I would just go ahead and do that, or the square root of 3. But they're not, so I don't have any perfect squares here. So what we're going to do is actually just multiply these through. So I'm going to combine these together under one radical and see if that can help me. And when I do that, I get 18, and then I get x squared. Now, 18 is not a perfect square, but it does have a perfect square factor, 9 times 2. 9 is that perfect square. And x squared is actually a perfect square. The interesting thing here is that the square root of x squared is just x. So that square root and that square are going to cancel each other out. So what we can do is, again, kind of split this into two parts. Split it into the parts that come out even and simplify completely, and then leave the other stuff kind of in their own root. So the things that are going to come out nice and even are going to be that 9 and that x squared. And then that root 2 is just going to end up hanging around. I can't really do anything with it. So here I have square root of 9 is 3. Square root of x squared is x. And we just have that root 2 there kind of hanging on. Now you can write it this way, or you can also write it 3 root 2 times x. Just make sure your x is not under the root when you write it. Sometimes when we're writing or typing, we forget to make that distinction. So you just want to be careful because in this case, that x is not under the root, it is outside the root. So more often than not, you'll tend to see roots written at the end of the answer just because it's easier. But this is also correct if you happen to write it that way. Okay. So I want to make a note here that when you have a square root and a square, they do always cancel out. So for instance, the square root of a squared is going to just be the absolute value of that answer, technically. So for instance, if you have the square root of 6 squared, the answer is just 6. And if you have the square root of -6 squared, the answer is also going to be 6 because we take that absolute value. So basically, your squares and your square roots are going to cancel each other out. They're opposite ideas, so they cancel each other out. Now, the reason why you take the absolute value, let's think about this. So let's pretend you didn't know this rule. What you would do is you would simplify on the inside first using order of operations. So something like this, 6 squared is just 36. And you can see the square root of 36 is 6, right? That matches. But here, -6 squared is -6 times -6, which is also positive 36. So this is why you're still getting that positive answer back out. So if you forget this rule or you forget that you have to take the absolute value all the time, just simplify under the root first and your answer will still work out. The big idea here to remember is that a square root and a square cancel each other out. So that's kind of like the big idea. Okay, so they're opposites, or what we call, usually we say inverses in math when we have opposites. Okay. Let's do a couple more examples. Now, again, we've seen a little bit of this already in a previous video, but let's kind of do a few more of these and really formalize this. So just like you have that product rule, we also have a quotient rule. And this says that if you have the square root of a quotient or a fraction, then you can, again, split that square root. So notice here that we're splitting roots for multiplication. So we have a product rule or for division, but we don't do it for adding and subtracting. So you just want to be really careful. We can only kind of split here in certain cases. So something like this, I can rewrite as the square root of 100 over the square root of 9, and then I can simplify each part separately. So this gives me 10 over 3. Or if I have something like the square root of 48x cubed over the square root of 6x. So here I'm starting with the two square roots separate. And if I look at 48 and 6, I don't really have any perfect squares there. It's kind of messy. So this is a good one to maybe bring back together. So you can go in either direction. You can split them apart or you can bring them back together. So here I'm going to bring it back together. I'm going to simplify under the root. So here you have 48 over 6. And 48 divided by 6 is going to be 8. And then think about your x's for a second. Let me write this off to the side. You have x cubed in the numerator over x. So you have 3 x's in the numerator and 1 in the denominator. So what you're going to notice is that one pair of x's cancel, and you have 2 x's left in the numerator. Well, x times x is x squared. So this just simplifies to x squared. Now this is a little bit easier to work with. 8, again, is not a perfect square, but it does have a perfect square factor. That 4 is a perfect square, so I can break it down. And x squared is nice because we've seen that a square and a square root are going to cancel. And we're going to assume here in our values that our x's are positive. So in that case. So I'm going to break this apart. So in my first root, I have the 4 and I have the x squared because those are both going to come out nice and even. And then I have a 2 here in the second root. So square root of 4 is 2, square root of x squared is just x, and then multiplied by that root 2. Now, the other thing I do want to clarify here that when you're using the quotient rules and you're using the product rule, I kind of skipped over this idea, but you are assuming that your values on the inside are not negative. So we are kind of making that assumption that we're not dealing with any negatives on the inside. So we do have that to be careful of here. So maybe I'll make a note, A and B are both greater or equal to 0. And then for this one, A and B are both greater than 0, greater than equal to 0, and B is not going to be 0 because we don't want to divide by B in the denominator. So we don't have the issue of x being negative here, which is why I'm not putting in the absolute value sign. And you're going to see a lot of times when you simplify problems, some of them will say assume x is non-negative so that you can just jump right in and write your answer. If you're not assuming that x is non-negative, then you would sometimes have to put that absolute value sign around, right? When we cancel out that square root, we do technically take the absolute value of the number that's inside. So x would be non-negative here. So either 0 or positive. The last thing I want to talk about in this video is I want to talk about adding and subtracting with radicals. So let's look at an example. Or I'll look at 2. And adding and subtracting radicals actually works very much like variables. We add or subtract like terms, we add or subtract like radicals. So like radicals would mean that you have the same exact root. So the same kind of root and the same thing underneath the root as well. So notice here that I have the same roots. They're both square root of 2. So what you do is you actually just work with the outside values. 7 plus 5. Well, 7 plus 5 is 12. And then you rewrite that root 2. And that's it. So just like if you had an x here, right? So it's similar to if you had 7x plus 5x, your answer would be 12x. You would just add the numbers and keep the x. We do the same thing here. We just add or subtract the numbers out front and we keep that root the same. Okay. For this one here, notice I have the same root, root 5x, root 5x. So as long as I have the same root, I can go ahead and add or subtract. If you don't have a number out front, you do have a 1 there. So you're actually looking at 1 minus 7, and 1 minus 7 is -6, and then you have that root 5x. Now, if you could simplify your root further, then you would go ahead and do that, but here we really can't simplify anything. Let's do another one of those, make it a little bit more challenging. So we're going to add or subtract. I'm just going to write simplify. So here again, we're adding and subtracting, and you might be noticing and saying, okay, but there's no like roots. How are we supposed to do this? And you want to remember that you should always simplify your roots first, if you can. In the last example, we really couldn't do anything. But here, now I can't do anything with root 3, but I can do something with root 12. Root 12 is the same thing as having 4 times 3. So I can rewrite this as root 4 times root 3. And now I can simplify. Root 4 is 2. So my problem actually becomes 7 root 3 plus 2 root 3. And now you can see that you have like roots or like radicals. So 7 plus 2 is 9, and my answer is 9 root 3. For the next answer, again, I don't have like radicals, so you're going to think about, can I simplify? And I can't do anything with the x, but I can do something with the 50. So 50 is 25 times 2. And then with 32, if I think about this one, it's actually 16 times 2. So what happens here for this root is you end up taking that root 25 out, and you're going to leave the 2 and the x underneath. And here you take the root 16 out and you leave the 2 and the x underneath. So I'm just separating out things that are perfect squares and things that are not going to cancel. So here I have a 5 root 2x, and then here I have a 4 root 2x. Now remember that this was just this part here. Right? So let me rewrite the problem. I had a 4 on the outside, and I'm multiplying that by 5 and then root 2x minus a 6 on the outside, and this part now became 4 root 2x. Let me make my root a little bit longer there. Now you multiply your outside numbers. 4 times 5 is 20. And 6 times 4 is 24. Okay. Notice that when I'm multiplying here, I'm just multiplying the outside. I'm not touching the inside of the root. Once the inside of the root is simplified, you usually don't want to touch it anymore. So here, now I'm going to go ahead and subtract 20 minus 24. It's going to be -4. And then I just have that 2x. And just be careful. So as I was writing, I noticed my roots were getting a little bit short. So it was hard to tell, is my x under the root or is it not? But for this problem, your x is definitely under the root. So just make sure, and I'm fixing them in mind too, that it's really clear that in this example, that x is underneath the root.